In this podcast, we're going to look at something called combinations of functions, and we're going to look at the functions combinations that consist of the four basic operations: adding, subtracting, multiplying, and dividing. Sometimes in math we find ourselves doing the same operations over and over, just with different numbers, and sometimes we can shorten that by going to these combination functions. Now, I want to explain some of the notation here. The name of the function is f plus g. That's why I put it in a bracket. I don't want you to get the idea that that's two separate functions. That's a new function formed from a previous function f and a previous function g. And to indicate that it's a single function, I put it in a bracket. Sometimes, however, you will see that notation without the bracket, but it's always pretty easy to tell when somebody is talking about a sum function. The definition that we have is the sum function f plus g of x is equal, by definition, that's what the equal d means, it equals by definition, to f of x plus g of x, just the way you'd think you might define a sum function. Now, when you form these functions, sometimes as you simplify, terms disappear that tell you important information about the domain. So it's very important to understand what the domain of each of these composite functions is. So here I've listed the domain of f plus g, DOM f plus g down there. And it says it's equal to, and this curly bracket means the set, or the set of all. So this says the domain of f plus g is equal to the set of all x such that means with the following properties. X is in, the little e means is an element of. X is in the domain of f, and x is in the domain of g. So what's a legal x that f plus g can operate on? Well, it has to be a legal x for f and a legal x for g, and then it's a legal x for f plus g. Now let's take a bit of a look at how this definition is actually used to evaluate functions. So suppose we have one function f of x, which is 2x plus 1, and another function g of x, which is 3x minus 4. What would the sum function f plus g be evaluated for the number 2? Well, according to our definition up here, f plus g of 2 is f of 2 plus g of 2. Now you can see what those numbers are just by looking at f and g. F of 2 is 2 times 2 plus 1, so that would be 5. G of 2 is 3 times 2 minus 4, so that would be 2. So f plus g of 2 would be 7. Let's go and take a look at a little bit more generalized example. This next one says find and simplify f plus g of x. What is its domain? Well, again, according to the definition, f plus g of x means f of x plus g of x. So this time I'll sub in the whole f of x, 2x plus 1, plus, and I'll put in the whole g of x, 3x minus 4, so we end up with 5x minus 3. Much easier than first computing 2x minus 1, then computing 3x minus 4, and then putting them together. Here we just have one formula to do to go straight to the answer. So that's why you use composite functions. Now the second part said, what is the domain of this f plus g? And our definition says x is in the domain of f plus g if it's in the domain of f and the domain of g. Well, think for a second about the domain of f. F of x up here is 2x plus 1. Its domain is all numbers. It's all numbers because you're not dividing, so you couldn't be dividing by 0, and you're not taking any square roots, so you couldn't be taking square roots of the negative numbers. The same holds for g, so both f and g have domain which is all real numbers, so we would say the domain of f plus g is all numbers. Now another way of saying all numbers would be in interval notation. We could say the domain is negative infinity to infinity, and that would be all numbers. Well, let's see. We've used up pretty close to half our podcast. The next thing we're going to do is we're going to look at an example using f and g of the difference function, which we're going to call f minus g of x. let's just go ahead and do that one now. Suppose we're asked to find f minus g of x. The definition, of course, is f minus g of x is f of x minus g of x if f of x and g of x are defined. In other words, for all x in the domain of f and for all x in the domain of g. It's the same definition as above, just stated in a slightly different way. So what would we do if we went for f of x is 2 times x squared plus 1 over x, and g of x is 2 over x? How could we write f minus g of x? Well, f minus g, evaluated at x, would equal to f of x minus g of x, which is just 2 over x. Let me do a little better job of that. And so if we distribute in the first one, that's 2x squared plus 2 over x, and then we subtract the second function, minus 2 over x, these zero each other out. So we end up with f minus g of x is just 2x squared, a very simple expression, which normally, if we were just to look at this expression to determine the domain of f minus g, if all we did was look at this, we'd say, well, all real numbers, because you're not dividing, so you're not dividing by 0. You're not taking any square roots, so you're not taking square roots of negative numbers. But we have to remember that f minus g of x is defined if both f of x and g of x are defined. Well, take a look at f of x. It's got this term in it, and g of x has this term in it, and both those terms are undefined if x is not 0, if x is equal to 0, because you can't divide by 0. So we have to say, even though this doesn't look this way, we have to say that the domain of f minus g is the set of all x such that x is not 0. Again, that doesn't show up after you've formed f minus g. You can only see it before f minus g is defined, but it is still a restriction on the domain of f minus g. And now I'm going to have to break here because I don't have enough time to finish this podcast, so just continue on with the next examples in part 2.